Okay, in the next section, I want to briefly discuss kind of another view that we can take of these Q-learning algorithms that maybe provides a little bit more of a unified perspective, because we covered lots of different variants. We covered fitted Q iteration, online Q-learning, deep Q-learning with replay buffers. We can unify all of these in one kind of conceptual framework, and I just want to highlight this in the next portion. And many of you might probably already suspect what that more general framework is, but let's just make it really explicit. So here is the general Q-learning with replay buffers and target networks that I discussed before. So here we have this outer loop where we save the target network parameters, phi prime goes to phi, and we could use this Polyak averaging trick or just a standard flip every n steps. In step 2, we collect some number of data points using some policy and add it to the buffer. In step 3, we sample a batch. In step 4, we take a gradient step, and then we alternate steps 3 and 4 some number of times. Now, this is written out here as a kind of a inner loop style algorithm, but it's really not. It's really a bunch of parallel processes. So the fitted Q iteration algorithm that we had before looks a little bit different. Here I've written it in a way so that it better resembles the version above, but you could also write it with supervised regression. So that one, we have the data collection in the outer loop, and then the networks are updated in the middle loop. But they're really kind of the same thing. And if you view them as having the same basic processes running in parallel at different rates, then all of these methods can be unified into one kind of parallel framework. So in the fitted Q iteration algorithm, the inner loop is just SGD. The DQN method that we had before is a special case where n equals 1 and k equals 1. But all of them are really just special cases of this more general view. So we have our data set of transitions, our replay buffer. This is the basic object at the center of all of this. We periodically interact with the world. And when we interact with the world, what we typically do is we take our latest vector phi, we construct some policy out of phi, for instance using epsilon greedy or Boltzmann exploration. We send it out into the world and it brings back one or more transitions. And you can think of this not as a discrete decision that we make periodically, but as a continuous process that is always running. So let's call it process 1, the data collection process. The data collection process takes steps in the environment, and each step it takes, it sends back to our replay buffer. Now, our replay buffer is of finite size. We can't just keep adding stuff to it forever. So we also have another process, an eviction process, which periodically throws things out of the buffer when it gets too big. There are a lot of decisions about how and when you throw things out, but a very simple and reasonable choice is to simply structure the replay buffer as a ring buffer, where the oldest thing in the buffer gets thrown out when a new thing gets added in. So if your buffer has 1 million transitions, then as soon as the 1,000,001th transition gets added in, then the oldest transition gets thrown in the garbage. And that ensures that your buffer doesn't grow unbounded. Then you have your target parameters phi prime, and your target parameters are used to compute those target values. And you have your current parameters phi. Your current parameters are the ones that you're going to give to process 1 in order to construct that epsilon greedy policy to collect more data. And you have a process 2 which updates the target values, the target parameters. So process 2 will periodically copy phi into phi prime or perform that Polyak averaging. And process 2 is typically a very slow process, so it typically runs very infrequently. And then you have process 3, which is kind of the main learning process. And what process 3 does is it loads a batch of transitions from the replay buffer, so that's step 3 in the pseudocode above. It loads in the target parameters, phi prime. It uses the target parameters to calculate target values for every transition in the batch that was sampled. It uses that to update the current parameters phi, that's step 4 above, and then saves them back out into the current parameters right there. So this is a kind of graphical depiction of a general Q-learning recipe that encompasses all of the algorithms we've discussed. All of them can essentially be instantiated as special cases of this general 3-process or 4-process if you also include eviction parallel architecture. And in fact, you could actually implement this as a parallel architecture. You could actually have these as separate processes in different threads, or you can implement it as a serial sequential process, but this mental model that there are really three different things that can all happen at different rates is still useful for thinking about it. So even though it seems like there are many different Q-learning algorithms, essentially they all just involve different decisions for the rates at which we run process 1, process 2, and process 3. So online Q-learning, the basic Watkins online Q-learning that we had in the previous lecture, is a special case where you evict immediately, meaning the size of your buffer is 1, it's a ring buffer of size 1, and then process 1, process 2, and process 3 all run at the same speed, and they all take one step sequentially. So process 1 takes one step, which means collect one transition. Process 2 takes one step, which means that your target values are always computed using the latest parameters. And then process 3 takes one step, which means that you make one gradient update. The DQN algorithm that we mentioned before is also pretty similar. Process 1 and process 3 run at the same speed, which is a slightly arbitrary choice when you think about it, because process 1 and process 3 are actually fairly decoupled, but they run at the same speed, so you always take one step of data collection and one step of gradient update. And then process 2 is very slow, and the replay buffer is quite large. So you might store up to 1 million transitions. Part of why this starts looking so weird is that when your replay buffer is large, process 1 and process 3 are pretty heavily decoupled. Because once it's large enough, the probability you'll sample the transition that you just collected becomes pretty low. It does turn out that it's actually quite important to collect data pretty quickly, so the performance of your Q-learning algorithm can degrade rapidly if you don't collect data fast enough, but nonetheless, process 1 and process 3 have, quite a bit of buffer space between them, literally. And then the theta Q-duration algorithm that I used for kind of illustrating these concepts can also be viewed as a special case of this. In theta Q-duration, process 3 is actually in the inner loop of process 2, which itself is in the inner loop of process 1. So in the theta Q-duration algorithm, you do your regression all the way to convergence, then you update your target network parameters, and you might alternate these a few times, and then in the outer loop, you pop all the way back out and collect more data. But these are really not all that different. They're just particular choices about the rates at which we run all these different processes. And there's something, of course, a little bit deeper about this, because for each of these processes, they each create non-stationarity for every other process. So if process 2 and process 1 are completely halted, then process 3 is just faced with a standard convergent supervised learning problem. So by varying the rates of these different processes, by making them all run at different rates, we're essentially mitigating the effects of non-stationarity. Because if the rate of process 2, for example, is very different from process 3, then process 3, which is running a lot faster, to it will kind of look like everything is almost stationary. So that's the kind of deeper reason why having these three different processes running at different rates can help Q-learning algorithms converge more effectively.